All right, and we're back. Hey, I'm getting close to 100 subscribers. Close to 100 subscribers. So make sure you subscribe. Section 4.1, matrices and data. Again, I love chapter 4. I love chapter 4, and I'm kind of getting like nostalgic about this because I think I talked to you guys. We're getting new books next year, like the Algebra 1, Geometry, and Algebra 2. We're all getting new books next year, and all of the books that we have, like that we're considering, don't have matrices in them. And that hurts me, because I love matrices and I think they're really cool and I think they're really beneficial, but they're technically not in the standards. Like they've been since we've gotten these books, they've been taken out of the standards. So like little by little, schools around us have started dropping it from the curriculum. Like Hoover didn't teach it, and then Jackson started not teaching it, and Leno started not teaching it. And it's like, oh man, we're the last ones. You guys get to know what matrices are. And the reason being is, matrices, it's just a unique, weird thing that only applies to a little piece of what we've been doing. It doesn't really apply to a lot of Algebra 2, okay? And by the end of this chapter, you'll know what matrices are, you'll know what matrices are used for, you'll be able to apply them. And in my opinion, they really aren't difficult. They're just brand new. It's something that you have not even seen before. Maybe some of you have seen before in comp sci, but it's something that you haven't even seen before. It's and I always liked that. I loved math classes in college because I loved the fact that there was still things that I learned. Like I thought I knew what I was doing, but there was still things that I could learn. There's still brand new things that I hadn't even thought about yet. And this is one of those things for you guys. Now, so what is a matrix? Well, a matrix is just a rectangular arrangement of numbers. It's a rectangular arrangement of numbers. How many of you guys have ever used Excel or Google Sheets? Everybody should be thinking, probably, right? You have used matrices. You have used matrices. If you have used Excel or Google Sheets or any type of number formatting software, right? That is basically a program designed to organize numbers in a rectangular pattern where you can assign rows, you can assign columns, and you can do operations on those rows and columns. Operations meaning add things together, subtract things together, find averages, find sums, whatever you needed to do. Okay, subtract one from the next to find the average of it, whatever. Those are examples of matrices. It's just a rectangular arrangement of numbers. That's what the word array means. Data can be presented in a table or spreadsheet as rows and columns of numbers. You can also use a matrix to show table data. A matrix is a rectangular array of numbers enclosed in brackets. Okay, so this is an example of a matrix. This matrix down here, we're going to call it matrix A for right now. Usually matrices are denoted by a capital letter. Okay, we're going to use matrices. We're going to denote matrices by a capital letter. So this is matrix A. Matrix A has 2 rows and 3 columns. Remember, rows go side to side, columns go up and down. Okay, so matrices have rows and columns. They could have any amount of rows and any amount of columns. You could have a really huge matrix, 100 rows, 100 columns, sure, whatever. You could have a really small matrix, a 1 by 1, 1 row, 1 column, just one piece of data sitting in there. Okay, you could have an arbitrary amount of rows and columns. Yeah, that if you decide to take this class called linear algebra in college, some of you might have to take it based on the major that you pick. If you take this class called linear algebra, just know that linear algebra just basically means it's a class about matrices. I actually think, yes, I do. I still have my linear algebra book. It's really thin, it's deceiving. It's like, oh, that must be an easy class because it's a thin book. Heck no. But yeah, this was a whole class about matrices. And how to apply them and how they relate to algebra. I'll keep that out for later. So you may take a class in college that requires you to have a basic understanding of matrices. Now, they'll probably start from scratch about what a matrix is anyway, because it's kind of grown out of the curriculum in high schools. But because we have studied this chapter, you'll be a leg up on everybody else if you have to take that class eventually. But again, a matrix is a rectangular array of numbers, has rows, has columns. Usually we denote it by a capital letter. The dimensions we would call an M by N matrix. An M by N matrix has M rows and N columns. It always goes rows, then columns. So for example, this is a 2 by 3 matrix because it has 2 rows, 3 columns. Rows go side to side, columns go up and down. Think of like columns of a building, right? Those go up and down. Okay, rows go side to side, columns go up and down. We would call this row 1. We would call this row 2. We would call this column 1, column 2, column 3. So yeah, A has dimensions 2 by 3. Each value in the matrix is called an entry within the matrix. Okay, each value, each piece of data in there is called an entry within the matrix. And each entry has its own address. Each entry has its own address. The address of any matrix is the location within the matrix. So the address of any entry is location in the matrix expressed by using the lowercase letter matrix letter. So for example, if I say this is matrix A, capital A, we would use a lowercase a and then a subscript with 2 numbers. Okay, the subscript going down and to the right of that letter, a subscript with 2 numbers, the numbers identifying the row and column of where that thing is. Like for example here, this 16.206 would be considered A21. Don't call that A21. That's not a 2-digit number. That are 2 1-digit numbers. A21. Okay? So that means I'm in matrix A. I want row 2, column 1. So within matrix A, I'm going to look for row 2, column 1. Right there. Gives me an exact location. For example, 17.668 would be A 2 3. Okay. If I wanted to know what value was at A12, I would say, okay, in matrix A, row 1, column 2, 16.29 would be A12. So the address is the subscript, like lowercase letter with a subscript, and that subscript, that 2 1-digit number, that tells you exactly where it is, the location within the matrix. All right, so we're just going to practice writing a matrix out right now. Prices for different sandwiches are presented on the right. Display the data in matrix form. Display the data in matrix form. So, I don't even have any markers up here. Hopefully. Okay, so here's our data. We've got, okay, if I want to use a matrix, you kind of remove all context from everything. You're only looking at the actual numbers of it. You're not actually thinking about what's going on within the table. So let's call this matrix, what do we call it later on? P. Let's call this matrix P for prices. Okay, well, if matrix P has 2 rows and 3 columns, so all we're doing is removing the context from the table and just basically putting it in brackets. 395, 595, 375, 560, 350, 525. Simple as that. It's basically a table with no lines or labels. That's the matrix. This is matrix P. Okay. What are the dimensions of P? Somebody tell me. 3, 2. 3 by 2. This is a 3 by 2 matrix. P 3 by 2. And that's how we can write it. I don't know if I said that earlier, but that's how we write the dimensions. Capital letter subscript dimensions. 3 by 2. Okay, so P is a 3 by 2 matrix. Okay, so what is the entry P32? What is the entry P32? 525. Yeah, row 3. Boom, boom, boom. Column 2. 525. So P32, and actually I should write it as a lowercase. Okay, lowercase p. P32, kind of hard to see without lines on it though. P32 is equal to $5.25. I'm looking row 3, column 2. All right. What is the address of 595? What is the address of 595? P12. Good. Row 1, column 2. P12. Again, a lot of this introductory section is a lot about just kind of like learning the language of it. Gotta learn how to talk about it. So let's start doing some operations. Let's start talking about adding and subtracting. Because I'll tell you right now, adding and subtracting, pretty easy with matrices. Now, there's only certain times when you can do adding and subtracting, and we'll talk about that in a minute. Okay, to add or subtract two matrices together, you basically add or subtract the corresponding entries. It's literally that simple. To add or subtract matrices together, you add or subtract the corresponding entries. So for example, do we see this 1 by 2 plus a 1 by 2? Right? We see a 1 row 2 column plus another 1 row 2 column. The answer is another 1 row 2 column. And I say, okay, well, if I'm just going to add together the corresponding entries, that means I'm going to add 1 plus 5 to get 6. And then I'm going to say 2 plus 10 to get 12. Simple as that. You add together corresponding entries. You add together entries that have the same address within their own matrix. Okay? So, the issue with that is, what happens if the dimensions are a mismatch? What happens if the dimensions don't match? Well, you can't add or subtract them. Okay? You cannot add or subtract them. If the dimensions do not match, you cannot add or subtract. So for example, I can add or subtract these ones. It's a 2 by 2 and a 2 by 2. Right? The answer would have been 3, 3, 13, 13. Right? You can add these. The answer would be 7, 14, 8. You cannot add or subtract these. This is a 1 by 2 plus a 2 by 1. This is a 1 by 2 plus a 1 by 3. I can't add or subtract those. The entries don't match. Okay? You have to have the exact same dimensions to add or subtract them. So my question is here. I've got W plus Y. First of all, can I add these together? Yes, I can. I can add these together. So let's do so. So we're going to take W, 3, 1, negative 2, 0, plus 1, 4, negative 2, 3. When you read them, there's really no rhyme or reason. You could read them going along the top row and then going to the next row. But really, if you read it from top down, it wouldn't be any different. You could say 3, 1, negative 2, 0. Just make sure that you're noting where things are. All right, so let's add these things together. A 2 by 2 plus a 2 by 2 yields me another 2 by 2. So let's add together corresponding entries. 3 and 1 make 4. Negative 2 and 4 make 2. 1 and negative 2 make 1 or negative 1. 0 and 3 make 3. Not so bad, right? Yeah. You could, but since I'm referencing W plus Y, we say W plus Y is this thing. Yeah. Okay, people. What's X plus Y? You can't do it. You can't do it because this is a 2 by 3 plus a 2 by 2. 2 by 3 plus a 2 by 2, which you cannot do. Can't do it. Can't do it. Undefined. The symbol, whatever you want to say there. Impossible. Questions about that? Okay. Next thing we're going to talk about is called scalar multiplication. Scalar multiplication. This is not multiplication of two matrices. Please know that. Multiplication of two matrices is a completely different animal. We'll talk about that on Monday. Okay. When I talk about scalar multiplication, it is just multiplying a number times a matrix. not a matrix times a matrix. It is a number times a matrix. You can multiply a matrix by a single number called a scalar to find the product of a scalar and a matrix, sometimes called the scalar product. Multiply each entry by the scalar. For example here, if I wanted to take 3r minus b, 3r minus b. Well, obviously here, I want to take 3 times every entry in my r, and then I want to subtract away p from it. Now, when I multiply by a scalar, it's not going to change the dimensions. So the dimensions of r are going to be the same as the dimensions of 3r. So I guess I should first ask, am I going to eventually be able to subtract these? Yes. 3 by 2 minus a 3 by 2. So yes, I can subtract these in the end. So let's actually calculate it out. So this is how we would write it. We would say 3 times matrix R, which is 1, negative 2, 0, 4, 3, 4, subtracted by matrix P, 3, 1, 2, negative 2, 0, negative 1. And then the next thing I would do is multiply in the 3. So this gives me 3, 12, negative 6, 9, 0, and 12. 3, 1, 2, negative 2, 0, negative 1. You're basically just distributing the scalar to all parts of the matrix. That scalar value of 3 just basically gets distributed to everything. 3 times 1 is 3, 3 times negative 2 is negative 6, and then 0, then we get the 12, the 9, and then the 12. And now at this point, we can subtract these, because again, they have the same dimensions. So this is going to be another 3 by 2. 3 minus 3 is 0. 12 minus negative 2 is 14. Be careful there, minus a negative. Negative 6 minus 1 is negative 7. 9 minus 0 is 9. 0 minus 2 is negative 2. 12 plus 1 is 13. Make sense? I mean, it's pretty simple as that. Bless you. You know, just adding or subtracting should be pretty easy. Okay, just adding or subtracting the corresponding entries. And if there aren't corresponding entries, you can't add or subtract. All right, let's take a look here. Use a scalar product to find the prices if a 10% discount is applied to the prices above. Now, I'll tell you this. When you have a lot of data and you want to do operations on that data, that's where matrices can be really helpful for you. Okay, and a lot of, using technology with matrices can be very helpful. Because if you've got a giant table of values and you just want to like multiply everything by 3, okay, you can do that really easily using a scalar product, okay, on a matrix. Okay, so t-shirt sizes. We got small, medium, large, extra large, and we got t-shirt and sweatshirt prices. So here's my matrix. We got 7.5, 8, 9, and 10. And then we've got 15, 17 and a half, 20, and 22 and a half. All right, so use the scalar product to find the prices if a 10% discount is applied to the prices above. What should I multiply by? Good, 0.9. 0.9. And it's 0.9 because I'm paying 90% of the total value, right? A 10% discount would be paying 90% of the total value. Could I really multiply by 0.1 if I really wanted to? Yeah, but then you'd have to take that 0.1 away from the original prices. You basically have to take that matrix minus 0.1 of itself, right? So in other words, we could just say 0.9 of itself. So we do that. We say 0.9 as a scalar product. Okay, 90% of all of these things. That will give me the 90%, the final price. Okay, final price, if the 10% discount is applied. Okay, so that means I'm going to take the same matrix here. Let's go through it and apply this. I've got 7.5 times 0.9, 6.75. I've got 0.9 times 8, so 7.20. I'll make it look like prices. 0.9 times 9 is 8.10. 0.9 times 10 is $9. 0.9 times 15, I don't know that now. $13.50. 0.9 times 17.5 is 15.75. 0.9 times 20 is $18. And, oops, 22.5 down here, I got too happy. 22.5. 0.9 times 22.5 gives me 20.25. So now I can look back at it and interpret this. I can say, okay, what's the t-shirt size, or sorry, excuse me, what's the t-shirt with an extra large discounted price? T-shirt with the first column, extra large with the last row, $9. What's the sweatshirt price, discounted price for a sweatshirt that's large? $18. So I can use the scalar product to kind of make my life a little easier. Yep. Okay, questions about that? Feel okay about that? Cool, I'm gonna give you 15 minutes to work on your homework, people. 15 minutes. 15 minutes. Whoa, thank you. So long, everybody at home. Thanks for watching. Don't forget to subscribe.